All right, good evening, everybody, and welcome to this month's meeting. It looks like it's going to be very interesting. I'm looking forward to it, since I have actually visited HES as well a couple of years ago. Peter, can you go ahead and introduce Professor Markus?
Yes.
Thanks.
Yeah. Good evening, everybody. It's a great pleasure to introduce to you tonight Professor Markus Böttcher from Northwest University. He's actually originally from Germany. And we are supposed to be colleagues, but I've met him before. But he's the South African Research Chair in High Energy Physics, occupying the position at Northwest University. And one of his pet projects is the HES Gamma Ray program in Namibia. So, Markus, very welcome, and please go ahead with your presentation.
Thank you for the introduction, and thanks for the invitation to speak here today. So yes, I will talk about gamma ray astronomy and what we do here in South Africa and Namibia in gamma ray and high energy astrophysics. So start out introducing what gamma rays are and how we do astronomy with gamma rays. So to start out, yes, most of you are familiar with the night sky. What we see in the night sky is, of course, only the light that we see with our bare eyes, that is visible light. So we see stars, we see plane of the Milky Way, but that's pretty much all we see with our own eyes. But the light we see is electromagnetic radiation, different colors that we perceive with our eyes, just corresponding to different wavelengths of this electromagnetic radiation, the electromagnetic waves that make up light. But the spectrum doesn't end where our eye's perception ends. So beyond the long wavelengths end, the red end of the visible spectrum, it goes on towards infrared and radio waves, towards short wavelengths or higher frequencies. It goes on to ultraviolet, X-rays, and gamma rays. So the key point that I'm making here is that the different wavelengths regimes correspond to different energies that the waves carry, that particles of light or photons are carrying. If we're talking about radio waves, we talk about the lowest energy radiation. If that was actually thermal radiation, it would correspond to something less than 100 Kelvin. It turns out in radio waves, actually, the concept of temperature does not really make sense. It's not actually reflecting a temperature, what we see in radio waves. It's different if we go to shorter wavelengths towards infrared. There's still longer wavelengths than visible light. There we're probing things that are a few hundred, maybe 1,000 degrees Kelvin warm or hot. That is primarily dust. So in infrared, we see primarily dust between the stars that's heated up by stars. In visible light, we see mostly stars, because stars have a characteristic surface temperature of a few thousand Kelvin. We know that the sun has a characteristic surface temperature of a bit less than 6,000 Kelvin, and most stars are like that. And this is why when we look up in the night sky, it's mostly stars that we see. At even higher energies, with probing higher temperatures than 100,000 degrees Kelvin, it's still mostly stars that we see there. It's just hotter, more massive stars than sun-like stars. We go to even higher energies at X-rays. We're probing things that are millions of degrees hot. That's often related to accretion of material onto a compact object like a neutron star or a black hole. At even higher energies, the temperature concept actually no longer makes sense. Typically, we're not actually probing things that are millions of, tens of, hundreds of millions of degrees hot. It's again things that are not really represented by temperature, but if it was, it would be probing things more than 10 billion degrees hot. So, as I said, light can be thought of as particles carrying the energy in the light. Invisible light that we see with our own eyes. The characteristic energy scale in physics used is an electron volt, the energy that an electron would gain when it undergoes a voltage drop of 1 volt. So 2-3 electron volt is characteristic energy of the visible light photon. If we go to shorter wavelengths or higher frequencies, get to ultraviolet, that carries 10 to 100 times the energy of visible light. X-rays, characteristically about 1,000 times. And in gamma rays, we're talking about 100,000, millions, billions, trillions, and even higher energies. There's really no end to that scale. And the most extreme recent result was by a Chinese instrument called LASO that has detected photons of peta-electron volt energies. So that's 10 to the 15 times the energy of visible light. So that's a quadrillion times the energy. So there's really no limit known to the energy that electromagnetic radiation can carry. So I'm sure you're all familiar with optical telescopes with which we observe from the ground visible light. That we can do because our atmosphere lets that energy through. But in most other wavelength bands, except for radio waves, atmosphere is actually absorbing this radiation. So if we want to observe in any other wavelength band, gamma rays, X-rays, ultraviolet, infrared, we have to go above the atmosphere to avoid that absorption. So with gamma rays, again, we're talking about photon energies above 50 keV, 50,000 times the energy of visible light, with no upper end, and frequencies not more than 10 to the 19 hertz. So as I said, to observe gamma rays in a characteristic energy range of maybe giga-electron volt, we really need to go above the atmosphere to avoid absorption by the atmosphere. So telescopes that we use across the electromagnetic spectrum to do astronomy. Of course, starting with radio, I'm pretty sure many of you are familiar with the Meerkat project in the Karoo near Carnarvon that will eventually grow into the Square Kilometer Array, the SKA. It's the largest man-made research infrastructure ever so far. So that we can do from the ground because the atmosphere lets radio waves through. In visible light in South Africa near Sutherland, I'm pretty sure many of you are familiar with it. We have the Southern African Large Telescope, SALT, and many other optical telescopes, again, astronomy that we can do from the ground. And SALT, in fact, is the largest single optical telescope in the Southern Hemisphere that we have right here in South Africa. In all other wavelength bands, almost all other wavelength bands, we need satellites, like, for example, the Spitzer infrared telescope that orbits the Earth. There's one example of an ultraviolet observatory in orbit. It's GALEX, the Galaxy Evolution Explorer. There are quite a number of X-ray telescopes out in space. Maybe the best resolution, the one with the best spatial resolution is Chandra X-ray Observatory that was launched in 1999. And the best thing we have in gamma ray astronomy of gamma rays with energies of about 1 billion times visible light, giga-electron volt. That's the Fermi Gamma Ray Space Telescope, launched in 2008. And as I'll explain in a little bit, at even higher energies, 2 trillion times the energy of visible light, we can actually go back to the ground, and I'll explain how that works. Because the gamma rays still don't get through, but we can still observe from the ground at these extreme energies. So you might wonder, why do we actually need to do astronomy in all these wavelength bands? Isn't it enough to just take a visible light image? We see everything we want to know. Like, is best answered by just looking at one individual object and just look at all the different wavelength bands, see if we actually see the same thing everywhere. So Centaurus A, the amateur astronomers amongst you may have already seen it with your own telescopes. It's not very difficult to find. If you have a large enough amateur telescope, go from Alpha Centauri to Omega Centauri, that same distance on, you get to Centaurus A. It's the nearest active galactic nucleus to Earth. What we see in visible light is, again, the light of stars. That is the central region obscured by a lane of dust. So this dust absorbs the visible light. That energy of the visible light heats that dust. And what this dust then does is, because it's getting hot from all the starlight that it absorbs, it re-radiates that in heat radiation that is infrared. So if we look at that same galaxy in infrared, it's actually the dust that shows up bright, and the stars and everything else really doesn't show up very much. So you see almost like a negative image of the image you see in visible light. Now go to even longer wavelengths, we see something like that. And it's not a wrong orientation or anything, it's actually the exact same object we see here. So The stars, the galaxy itself, really doesn't show up at all here, but what shows up is some outflows, jets, a pair of jets perpendicular to the plane of the galaxy. So that was towards longer wavelengths, lower energies. If we go towards higher energies, from the visible light to infrared, the picture still looks very similar. In fact, we only see hotter, more massive stars, but also ultraviolet gets absorbed by gas and dust. But if we go to X-rays, again, we see completely different things here. We don't see much from the galaxy in itself. These funny jets show up again. And we see X-rays from very hot, millions of degrees hot gas that has been expelled from the plane of the galaxy, maybe by supernova explosions, or maybe even by this active galactic nucleus that's there in the center. If we go to gamma rays, in fact, Centaurus A is the only object outside of our own Milky Way that gamma ray telescopes have, in fact, spatially resolved. For all other things outside of our Milky Way, we just see a point. We look at radio telescopes and at gamma ray telescopes. Here you see, well, in the background, still the visible light image, and everything, the blue in blue here, that is actually the distribution of gamma rays that the Fermi Gamma Ray Space Telescope is seeing. If we go to even higher energies, essentially everything we see outside of our galaxy is just a point. So this is really just not resolved. We see a source with HAC, so this is an image by HAC. We see that there is a very high energy gamma ray source, but it's barely resolved. That's actually one of the most recent results from HAC, that we have actually resolved this in gamma rays, but only just barely. So let me talk a little bit about different telescopes, in particular Fermi-LAT and HAC. So Fermi-LAT, Large Area Telescope, named after Enrico Fermi, of course, the Fermi Gamma Ray Space Telescope, was launched in June 2008. So it's been in orbit now for over 15 years. And it operates in a way that, not like you would do with an optical telescope, you point to a certain source, take your exposure, then point to another source. This operates in a slewing mode. It is, of course, in an Earth orbit. It's a satellite in a 90-minute orbit, and it points towards the northern hemisphere of the sky for one orbit, scans the entire northern hemisphere, then it slews down to the southern hemisphere, scans the entire southern hemisphere, and slews back up. So every 3 hours, we get the full view of the entire sky in gamma rays from Fermi. Now, most of you have probably seen the telescope before, and consider me crazy if I'm claiming that this thing here is a telescope, but it actually is, and it does it. And it has to do it in this way because gamma rays cannot be focused like you do with a mirror in a telescope. Gamma rays will just go through everything. But what these gamma rays do at high enough energies, they interact with material and can produce an electron-positron pair. So if a gamma ray goes into this telescope, it hits these conversion layers in the telescope, and then that's pair production in the electric field of a nucleus that produces an electron-positron pair. The electron-positron pair can easily be tracked. And of course, they carry the energy from the original gamma ray photon. They go in the direction in which the gamma ray photon has come in. And so we can measure first the direction where the gamma ray came from. And ultimately, down below, we measure the energy that they have, the calorimeter. So we can measure the photon energy at direction. That's precisely what a telescope was supposed to do. So this is how Fermi-LAT works as a gamma ray telescope. Maybe a little bit to the processes. How do things in the universe make gamma rays? So gamma rays have these extreme energies. So obviously, we need particles, elementary particles, that have at least those energies to make those gamma rays. So one way that's very common to make gamma rays in astrophysical sources is that we have extremely high energy, very highly relativistic energies. So with Lorentz factors, so some of you are familiar with relativity. Nothing can move faster than the speed of light, but these electrons approach the speed of light very, very, very closely, so that their total energy is actually thousands to millions of times larger than the rest energy, mc squared. so giga-electron volt to tera-electron volt energies. And if those interact with low energy photons, like the visible light photon, it can upscatter this photon to very high energies and produce gamma rays that way. And that is one of the most common mechanisms through which sources make gamma rays. So for that, we need these extremely highly relativistic electrons. Alternatively, this can happen with protons, so the nuclei of a hydrogen atom. If they interact with another nucleus or with another photon, they can produce secondary particles called pions. Pions are unstable and decay. And the decay products are either two photons, that were gamma ray photons, or if they're charged pions, they produce secondary particles, including neutrinos. But that would be an entire different talk if I was talking about neutrinos. So in this talk, we're only dealing with the gamma rays. But in order for that to really make these very high energy gamma rays that we see with Fermi-Lat and also with HAC, we need protons that have energies of tera-electron volt to octa-electron volts. That's 10 to the 18 electron volts. I guess that's a quintillion times the energy of visible light. And that is, in fact, more than 1 million times better than the best man-made particle accelerator, the Large Hadron Collider at CERN, can do. So we may be proud about the big particle accelerators that mankind has managed to fabricate, but nature actually just laughs at that because it can naturally do 1 million times better than that. So the upshot of this is that we do gamma ray astronomy. We're probing the most efficient particle accelerators in the universe, and in that sense, we're probing the most violent places in the universe. So hence the title of the talk, The Violent Universe. So if we look at this all-sky map that Fermi-Lat has now produced in 15 years, we see a map like this. This is projected along the plane of the Milky Way. So from left to right, we see the plane of our Milky Way, and the center is the center of our Milky Way. The left and right is the anti-center going away from the center of the Milky Way. And then we get to the galactic poles, 90 degrees up and down. The first thing that stands out, of course, is this bright band of the Milky Way. And this is this reaction that I've just talked about of very energetic protons, cosmic rays, hitting the gas between stars, the interstellar medium, producing pions, they decay and make gamma rays. So this is what we see as a diffuse background that essentially traces the gas between stars in the Milky Way. But then there's a lot of individual point sources, which is what I will talk about in a little more detail later on. So one source class called pulsars. I said I will discuss what all these are. These are collapsed, compact remnants of supernova explosions. There are sources related to supernova explosions, the remnants of supernova explosions, the ejected shells, like, for example, the Crab Nebula, probably the most prominent example. There are things related to binary systems with a black hole or a neutron star in the binary system with a normal star, where it pulls over material from that normal star, accretes it onto itself, heats it up, sometimes ejects these jets along with that process. Then there are things outside of our Milky Way. So these three classes I've just mentioned briefly are all within our own Milky Way. We do not see these outside of the Milky Way or the Magellanic Clouds. Outside, we see other galaxies, in particular quasars or HAC objects. These are dominated by these relativistic jets pointing close to our line of sight. I'll discuss these in a little bit as well. And then there are also active galactic nuclei like Centaurus A that we had this multi-wavelength view at the beginning of the talk. Some of these are also detected in gamma rays. So you see there's quite a zoo of different sources that actually manage to accelerate particles to these extreme energies, much better than we can do in man-made accelerators. Now let's go to even higher energies. As I said, Fermi-Lat detects energies of GeV, so about 1 billion times visible light. At even higher energies, 100 billion to trillion times visible light. We can go back to the ground, because even though these photons are absorbed in the atmosphere, they have so much energy that, well, they produce secondary electrons, positrons. These electrons and positrons have so much energy that they produce more gamma rays that get absorbed again, produce more pairs, more gamma rays, more pairs. You produce a whole shower of secondary particles, of thousands of particles, that all move extremely rapidly through the atmosphere, produce short flashes of Cherenkov light. And these telescopes on the ground, including HAC, are optimized with their cameras to detect these extremely short, just nanosecond short flashes of Cherenkov light. They would actually, they're not even that faint. If they would hold on for minutes or so, you could actually see them barely with your bare eyes. It's only that your eyes can't pick anything up that only flashes up for a few nanoseconds. So that's why we need big telescopes to observe these. There are three main facilities operating in this mode of Cherenkov gamma ray detection. There's one in the US called Veritas, the Very Energetic Radiation Imaging Telescope Array System. It's 4 telescopes of 12-meter diameters, located just south of Tucson, Arizona. Then there's MAGIC, a major atmospheric gamma ray imaging Cherenkov telescope. That's 2 17-meter telescopes on the Canary Island of La Palma. And of course, sorry, I don't know why it's doing this. Sorry about that. It's back. And there's HAC, the high energy stereoscopic system in Namibia that I'll talk about a bit more right now. That's like Veritas for 12-meter telescopes, but in the middle, there's a 28-meter telescope that is the largest Cherenkov telescope existing in the world. So again, for 12-meter, 28-meter telescopes, it's about 120, 140 kilometers southwest of Windhoek, Namibia. I'll say at the end, if you're interested in visiting, is how to reach it. It is the world's largest gamma ray observatory currently existing. It's operated by a collaboration of about 260 scientists, primarily from Europe. The biggest contributions actually made by Germany and France, but Namibia and South Africa are also very much involved there. There's about 4 institutions in South Africa and Namibia as members, and we are organized in a program called the South African Gamma Ray Astronomy Program that organizes and funds through the Department of Science and Innovation and the National Research Foundation of South Africa, our participation in HAC and also the next generation Cherenkov telescope array. It's about 100 members at 6 institutions in South Africa and Namibia, and I'm chairing this consortium since 2013. And the whole sky map of the very high energy gamma ray sky looks very similar to what Fermi's lattice sees. We see a lot of sources in the Milky Way, in the plane of the Milky Way, like these pulsar winds, pulsars, pulsar wind nebulae, binary systems, and active galaxies outside of the plane of the Milky Way. Now let's talk a little bit about the individual sources here. So one is remnants, as many of you know, very massive stars over solar masses end their lives in very massive explosions, with the core collapsing to a star. I'll talk about those in a minute as well. And the outer shells being ejected and slamming into the interstellar medium, using powerful shock waves. And that's these shocks of this ejecta with the interstellar medium that manage to accelerate particles to extreme energies. Best example, I think, is the Crab Nebula, so the remnant of a supernova explosion year 1054, recorded by Chinese astronomers. This is actually a very bright gamma ray source and often used as a standard candle because it produces a very known, usually steady gamma ray flux. I was actually a bit surprised a couple of years ago when it turned out that in Fermi gamma rays, it's actually not as steady as we thought it was. But in very high energy gamma rays, it's a very steady source and often used to calibrate gamma ray fluxes of other sources. Another example here of an X-ray image of a supernova remnant. I believe this is from the Chandra X-ray Observatory. So you see a nice round structure of these supernova ejecta and some very turbulent structures because, well, obviously nothing is really uniform. So there's instabilities forming, giving this interesting structures. And interesting because this is one of the very few types of sources that we can actually resolve spatially in gamma rays. So one of the few sources where it actually makes sense to show an image. So this is a HAC image of one prominent supernova remnant with a telephone number named up here. Now, in addition to these supernova remnants, what supernova explosions produce is the compact core of the star. Not the whole star explodes. The very inner regions of the star, where the star at the end of its life has finally produced iron and even heavier elements like nickel. So this collapses down to an extremely compact object. And as it had some original rotation, if something is rotating and it suddenly collapses, this rotation speeds up dramatically. At the same time, also magnetic fields that were present in the star get compressed to extreme values. So these neutron stars, as we call them, are characterized by there no longer being normal matter with nuclei and electrons around them. It's all squeezed in together to essentially nuclei and subnuclear particles, actually. So that's about 1.4 to 3 solar masses compressed down into the size of only about 10 kilometers. So that means densities that are much larger even than the densities in an atomic nucleus, which then means that if you had a teaspoonful of neutron star material, it would weigh about 2 billion tons here on Earth. This does not include the weight of the teaspoon. It has rotation periods that go down from a few milliseconds, extremely fast rotations, up to a few seconds. And magnetic fields are the highest that we find anywhere in the universe, from 10 to the 8, so 100 million to 10 to the 15 Gauss. For comparison, the sun has characteristic magnetic fields of a few Gauss, just like typical magnetic fields on Earth are. So these are 100 millions to trillion times higher. So now these have very strong magnetic fields, rotate very rapidly. So we have these dipole magnetic field structures similar to the Earth's magnetic field, but it's very violent, fast rotation. So that produces often beams of radiation, sometimes along the axis of this magnetic field structure, sometimes also in other directions. And if we happen to lie in the path that this beam traces out in the sky, then every time the beam hits us, we see a little blip of radiation. That's why these systems are called pulsars, because they're very naturally, very constantly pulsing systems. That's, of course, the kind of thing that people in SETI are looking for, these unnaturally looking periodic signals that no natural phenomenon can obviously produce. That's actually when they were discovered in the 1960s. They were first named as LGM1, LGM2 for Little Green Man 1, Little Green Man 2. But very soon people realized that this is actually just the signatures of these rapidly rotating neutron stars. And so what accelerates particles here most likely is closely related to these extremely strong magnetic fields. Strong magnetic fields that are not aligned with the rotation axis. So these magnetic fields are really swirling around with extremely rapid speed, and very rapidly changing magnetic fields produce electric fields. Electric fields are very good to accelerate particles to extreme energies. Most likely that is at least one mechanism that is responsible for accelerating particles here so that they can produce gamma rays at these extreme energies. Maybe a recent highlights that we have produced with HAC was that we have seen one particular pulsar, namely the Böttcher pulsar, at extremely high energy. So they have been seen to pulsate from radio to optical X-rays, gamma rays by Fermi-Lat. but it was the first time that we saw them at extreme energies above 20 tera-electron volt, 20 trillion times the energy of visible light. So this is a very recent result. You can see here, this illustrates that the pulse that we see, so this is the light curve essentially, so the brightness of the gamma rays as a function of time folded throughout this rotation period. So from left to right, we go from one starting of the period to end of the period. So this is something that will be published in Nature Astronomy in September this year. So in addition to just accelerating particles in this very strong magnetic field, somehow these pulsars also manage to drive particles away. So drive winds that move with almost the speed of light away from the pulsar and then slam into the surrounding medium. You see this here as an example of the Crab pulsar, so the center of the Crab nebula, where you see this is a repeating sequence. One sequence is about 8 years in real time. So it's, of course, very much sped up. But you can actually see stuff, you can actually see shocks moving out from these pulsar winds that the pulsar is driving away at almost the speed of light. And there's quite a number of pulsar wind nebulae, as we call them, that are seen in TeV gamma rays by HAC and other ground-based Cherenkov telescopes. It's a very large source population. Next source class that I will not talk very much about is binary systems. So systems where, for example, we have a very massive star and a neutron star. They orbit each other. A neutron star, as we said, has about 1.43 solar masses. A massive star in one particular system that is illustrated here has actually a much larger mass, I believe about 40 solar masses, and it drives gas actually away from the star. So it's a disk of material that has been driven out by the rapid rotation of the star. And when the neutron star then passes through this disk, it accelerates particles as well. It produces shocks there from pulsar wind that's produced with this ejector. And that is one source of gamma rays. So there's one very famous binary system like this, but this is very periodically observed every about 3.4 years. The pulsar crosses this disk and we see bright flare and X-rays and gamma rays from this source. Now, these were all sources within our own Milky Way. Let's talk a little bit about sources that are outside of our Milky Way, so related to other galaxies. And there, the most prominent source class is called active galactic nuclei, or AGN. So in these AGN, like in most galaxies, there's a very massive black hole in the center. So masses of millions to billions of times the mass of the sun. So we know that pretty much all, as far as we know, all galaxies, including our own Milky Way, have a supermassive black hole in the center. Our own Milky Way has a black hole of only about 4 million solar masses. There are other galaxies that have much more massive black holes. But in our own galaxy, there's almost no gas in the vicinity that the black hole could swallow. So the black hole in our own Milky Way is actually a very, very faint source of X-rays and gamma rays. It's almost not radiating anything. But of course, there are galaxies, in particular galaxies that have interacted with other galaxies in the last couple of million years. And there is a lot of gas to accrete. So if gas accretes, it has some sense of rotation around the black hole. So it forms an accretion disk. It collapses perpendicular to that, forms a disk. And through processes that are still not quite understood, it's not only swallowing gas inward, but it also ejects gas along these streams of gas perpendicular to the disk. These streams, we know now, are moving essentially with the speed of light with Lorentz factors of 10 or 20 or so. I'll say in a minute how we know that. And those are the sources where we actually, the universe actually produces these extremely high energy particles that make gamma rays. Almost all sources that we see in gamma rays outside of our Milky Way are these jet-dominated active galactic nuclei. So what we see, if we look at them now with radio waves, is that we can actually resolve these jets. And now it looks like there's only one jet here. So that's the center of the galaxy here. There's one jet going towards us. And it only looks like there's one jet. Obviously, this can't really be that it only ejects things in one direction, but not in the other one. But this jet, as we know now, is directed at a very small angle towards our line of sight. It's directed almost straight at Earth. And that means relativistic effects, relativistic aberration, relativistic Doppler boosting leads to a strong enhancement of the radiation that we see from this jet. So the jet appears actually much brighter than it actually would look like if the stuff wasn't moving towards us. So this is strongly enhanced. There's some kind of relativistic aberration, is a relativistic beaming effect that all the radiation is bunched up in the forward direction in which the emission region is moving. The same jet goes in the other direction, but there the light, radio waves, gamma rays are beamed away in the opposite direction. So it seems much fainter than the jet pointing towards us. So that's why we get this impression of there only being one jet, because there are two, but we only see the one that's beamed and enhanced towards us. There's also radio galaxies where the jet is not really pointing towards us. And Sen A that we've already talked a bit about is one of the very few examples where even without this relativistic boosting and beaming, we can actually see gamma rays, and in this case, even spatially resolve the gamma rays. Now, one funny effect that actually tells us precisely that we're dealing with a jet pointing almost at our line of sight. We can see if we follow these jets in very high resolution radio images through interferometry, radio interferometry. You follow the jet structures over many years. You can see here at the top time clicking 2005, 2006, 2007, and so on. So taking regular pictures, there's a very intense monitoring program called Mojave that is using telescopes in the US and to do these observations on a regular schedule. So you see a very bright core where probably the black hole is sitting, the central black hole. And then you see individual components, blobs moving along these jets. And the funny thing is, though we know how far away this source is, this is actually a very well-known source. Look at the catalog number here. Many of you may know the source as 3C273. So a very famous quasar, in fact, the first quasar ever detected as a quasar. So we know how far away this is. If we know the angular separation as a function of time, we can calculate what speed that corresponds to. And if you do that calculation, you find in many sources that this is 10, 20, 30 times the speed of light, or even more. So does that now mean that relativity is wrong? Luckily not, otherwise we'd have to redo a lot of physics. The truth is that we're dealing with something that emits this radiation, the radio waves, moving along the jet. And the jet is directed at a very small angle towards us. So we are very far away on the right. And because this is moving with almost the speed of light, it is just almost catching up with all the radio waves and the light that it has just emitted. So the time that actually elapses from the beginning of this ejection here to it reaching the end of the error here is much longer than the time in which we actually see all the radiation bunched up just a little bit in front of this emission region. So we see this motion on a much, much shorter time than actually has elapsed. Now, seeing the same motion on a shorter time means we see a much larger velocity than it actually is. But this really tells us that we're dealing with things moving along the jet with Lorentz factors of 10, 20, 30 or so, and moving almost at our line of sight. And that means that all these weird relativity effects of beaming and boosting so strongly enhance the radiation that we see. And this is why we see these as so bright gamma ray sources. Now, last I want to talk about is not steady sources. So many sources that we see with gamma rays are actually not just staying at the same brightness all the time. That's definitely the case for these active galaxies. Could talk much more about that. But there are also transient sources, meaning sources that in the gamma ray sky just only shoot up for a short amount of time and then never again. In particular, these are gamma ray bursts, so really short flashes of gamma rays that just show up for just seconds up to maybe minutes or 2 or 3, and then we never see anything again from them. They were in fact detected in gamma rays first, and it has taken almost 30 years from the first gamma ray burst detections in the late 1960s until finally actually these were also seen to emit over longer time scales at longer wavelengths, so in X-rays and then later also in optical and radio. So it really took from the late 1960s up to 1997 until finally the first counterparts in other wavelengths were seen. So there are 2 classes of gamma ray bursts that we see that are really distinct types of bursts. Some called long gamma ray bursts that actually last for typically a few seconds to a minute or 3 minutes, 4 minutes, and then fade away. Those are the ones from which we mostly see these afterglows over hours, days, and then weeks in radio, sometimes even months later, gradually decaying away. And then there are short gamma ray bursts that only show up for less than 2 seconds, many of them really just flipping up for milliseconds and then being gone. For many of these, we don't see any afterglows either. So they have been detected actually in soft gamma rays. So most of the emission comes out at a few hundreds of kilo electron volts, so kind of at the boundary between X-rays and gamma rays. Only very few of them show up in higher energy gamma rays. And as I'll show in a minute, it was one of the big breakthroughs in understanding gamma ray bursts that even with ground-based Cherenkov telescopes, we have now seen actually firmly detected 4 gamma ray bursts. These are long gamma ray bursts. Long gamma ray bursts are believed to be produced by extreme versions of supernova explosions. So it's a very, very massive star. Most likely you need a star more than 25 solar masses that collapses to such a massive compact object that it's too heavy to be a neutron star. It collapses straight to a black hole. And then this black hole, well, there's no hard surface for things to bounce off to produce a good supernova. So much of the material actually, instead of bouncing off and producing that supernova remnant, actually falls in and produces a very massive accretion onto this newly formed black hole. And just like in active galactic nuclei, if there's accretion, very rapid accretion onto a black hole, it also ejects jets. In this case, we know these jets can be even much faster than those in active galaxies. It can reach Lorentz factors of 100 or thousands or so. And if those are happening to point towards our line of sight, we see these bright gamma ray bursts that then gradually, as stuff that ejects along the jet, is slowing down and gradually cooling down a little bit to emit at longer and longer wavelengths as time goes on. Now, a big new result that we've produced with HAC very recently was from a gamma ray burst in 2019. Gamma ray bursts are named essentially just by the date on which they've been detected. So this was 2019, sorry, 0829, that's supposed to be not 80. It was 2019, August 29. Where HAC wasn't actually able to point towards it directly because it was actually below the horizon, but we pointed towards it a little bit later, detected it, pointed again the next day, detected it still, and even third day after, we still detected it. So remember, these are short explosions that were known to show up in gamma rays only for up to maybe a minute or 2 or so. So this discovery that there's actually this long-lasting afterglow, that the shock that's produced by what's ever shooting out along the jet is still producing these extremely high energy particles even 3 days later. This was a very new result that has been published in Science in 2021. Now there's short gamma ray bursts that only show up for less than a second typically. Those are now pretty well understood to be the mergers of two neutron stars. So two neutron stars that actually lose energy. They lose energy by gravitational waves. Many of you may have heard another breakthrough that I could give another entire talk about, of detection of gravitational waves that we see when space-time is distorted by rapidly moving, very massive objects. So interactions of merging of two neutron stars or two black holes are the prime candidates of sources of gravitational waves. And it has long been speculated that gamma ray bursts are produced by these mergers, and they should be associated with gravitational waves from exactly this same merging event. And another really big breakthrough, what's called this breakthrough of the year 2017 by Science Magazine and Physics World in 2017, was in fact this discovery that there was a neutron star merger seen in gravitational waves. So you see down here below the gravitational wave signature detected by LIGO in the US. You can see the frequency of these gravitational waves getting higher and higher and higher as they merge closer and closer. The orbit gets faster and faster until the merging actually happens. And then it takes about 1.4 seconds until this newly formed object finally collapses and produces a gamma ray burst in the process by ejecting the rest of the material that doesn't collapse into what is probably now a black hole. So this combined observation of this gravitational wave source and this short gamma ray burst really now confirmed that the short gamma ray bursts really are the sources of gravitational waves and are caused by neutron star merger. So, well, HAC, of course, pretty much every astronomer in the world was interested in this. I think everybody who could observe this in various wavelengths, X-ray, optical, infrared, radio, and gamma rays. Of course, the paper reporting this had 3,677 authors. I'm one of them. And so this was actually associated then also with the ejecta called a kilonova. That is a kind of supernova explosion that is expected to come from this kind of neutron star mergers, where you have very heavy metals interacting with each other, producing even heavier metals, like the noble metals, most of the gold, for example, that we have in the universe, all of gold that we have in the universe, probably was produced in one of these kilonova events. So this was detected in a galaxy, the catalog name you see here, at a distance of about 42.5 megaparsec. And now, interesting thing with HAC is that we actually, pretty much by luck, managed to be the first telescope on the ground to point in exactly the right spot. Because these transient events, you never know where they're going to happen. So it's always difficult to pinpoint, to have a telescope that, first of all, observes enough of the sky to see the event, but at the same time is able to pinpoint well enough where the event actually is. So there was actually quite a large error region in which the event could have been, that you can see here on the left. And with the test, we were lucky enough to point at it at 5.3 hours after the merger. Unfortunately, we didn't see anything, but still we were able to put very stringent constraints on very high energy gamma ray emission that could have been produced by this merger. That brings me to the end of my talk. Maybe just a quick mention of where HAC is located in case some of you make it to Windhoek at some point and are interested in visiting. Always happy to have visitors there. It's about 120 kilometers southwest of Windhoek. We just go out along the C26. After about 120 kilometers, you see a turn off to the right. You see a small sign saying HAC to the right. If you wish to visit, you're always welcome, but please pre-arrange, because it can always be that it's not possible to visit if you show up unannounced. So please pre-arrange if you wish to with the site manager, Tony Hanke. Here's the contact with which you can reach him. This is recorded, so you can always look this up later. Thank you.
Wonderful. Thank you very much. Fascinating talk. Can we ask the audience to ask any questions they now might have? I've got a small one if nobody else has got one. Okay, can I just kick off?
Thoroughly impressed with the slides. Fantastic graphics. Thank you.
Thank you. I didn't make them, though.
Yeah, fantastic.
Can I just ask a quick question, Markus? The comparison of the Fermi Gamma Ray Telescope compared to the resolution of HAC. I know they work on different sort of observing principles, but which is better? Which is able to have a better resolution or show better detail?
They're actually comparable. They're both about 0.1 degrees in both cases.
Okay.
So compared to optical or radio astronomy, it's very poor resolution. So for Fermi, it gets better with energy. As the higher the energy, the closer the electron and positron are staying in the forward direction, so the better the energy resolution. With HAC, it's not that much dependent on the energy, but it's in both cases about 0.1 degree.
I've just been wondering, it's a little bit off topic probably, but with the very high frequency of the gamma rays, has anybody managed to figure out a way to transmit gamma rays and use that to transmit obviously a very high amount of information?
Well,
you know anything like that?
The problem would be the detection, and the problem also is you're not really seeing signatures that are characteristic of the wave image of light. So it's really the particle image. We detect individual photons, so that would make that not really feasible.
Okay, Chris, I see you've got a raised hand.
Yes, thank you. This is really, really fascinating. I don't know whether to be more impressed by the intricate physics or the fact that mankind has managed to actually understand this stuff and create probes that allow us to delve deeper. My question is it likely that HAC will be expanded to have like a long baseline that will enable the narrower field of view, a higher resolution?
No, there will definitely not be an expansion of HAC, but there is the next generation Cherenkov telescope array actually now starting construction. So that will be in 2 sites. Could give it a whole different talk about CTA, but that is a worldwide effort by, I think, 31 countries all over the world. That will be built on 2 sites, one in Chile, in Mount Paranal, so near where the EELT is being built right now. And there's a northern site on the Canary Island of La Palma, actually on the site where the MAGIC telescopes are right now. So the ultimate goal was to actually have an array of up to 100 Cherenkov telescopes over a much larger area with 3 different sizes. So when large size telescopes optimize to observe at even lower energies towards the Fermi energy range than we can currently do on a relatively small, probably only 4 at each site optimally. And then smaller telescopes on a much, much larger array of like 10 square kilometers for extremely high energy gamma rays. Of course, there are very few, but these gamma rays produce pretty bright showers, so we don't need big telescopes to observe these. But since there are so few, we need a huge area to actually cover that. So this is going on, this is happening. It will be built first now at a reduced configuration, but that will still significantly exceed the capabilities of all currently existing telescopes. But probably it'll be more like 2028 or so before that is fully operational.
Thank you.
Okay, thanks. Anybody else?
Can I ask a question? The Big Bang was a high energy event. Were there any gamma rays produced at that time that can be detected?
I mean, the Big Bang produced everything that we have here right now. In fact, what we see today as the cosmic microwave background is essentially what was produced. The universe started extremely hot. Of course, there was plenty of gamma rays up to, well, there's no upper limit, depending on how far you go back towards the Big Bang. So originally, everything started out with just a mix of particles and extremely high energy gamma rays that were constantly annihilating into each other. So obviously there were, but whatever is left over of that is now the cosmic microwave background. So it's expanded by cosmic expansion, obviously.
Yeah, so the redshift has lengthened the gamma ray frequency of the original frequency.
Yes, right. But that decoupling happened at a redshift of, what was it, about 1000 or so. And there, so see the 3 Kelvin now, there was about 3000 Kelvin. So even back then, it was still only infrared. So whatever was there originally in gamma rays essentially all just annihilated and produced electron-positron pairs and expanded further out until it actually decoupled from the material, from the matter.
Okay. It seems like you have given such a good explanation of your topic that not many people have questions. Either that or they're a little bit mind-boggled. Go on, who we got here? Is Peter still with us, or no, Peter's left? Okay. Unfortunately, he's busy with conferences and things. Maybe have you unshared there? Okay. All right. If there are no more questions, I'm going to say thanks very much for a very fascinating topic. I'll send you a link to the YouTube recording once I've done that in a day or two, so that you can see it if you want. And I must say then, thanks everybody for your attendance, and thanks very much for the fascinating presentation. I'm definitely going to look at it a couple of times myself. It's too much to take in just at the speed that you presented it.
Yeah, right. Not something that one usually deals with as amateur astronomers.
Thanks very much.
Yes.
Very
Yes,
kind.
thanks for the invitation.
All right.
Bye.
That was excellent.
Thanks for everybody. I'm going to stop the recording now and log off.
Okay. Bye.
Goodbye.